So Wendy, you've not been on a podcast before, huh?
I have not. Thank you.
Yeah, well,
What? She's all turned in pink now. Good job, Johann.
yeah, well, we've not had a guest before either, so it's a first for both of us. So
Perfect.
yeah, well, we're glad you're here. I am curious because how in the world did you get started? What brought you to Silicon?
So that's a great story. I never thought that I wanted to do anything with research. I love science, I love plants, so I wanted something where I could be outside. So I was looking for park ranger, something that I would not be stuck inside in a lab all day long. But I did my senior year of my undergrad, decided that I would try doing a research lab. So I got started at the University of Toledo in a lab and was doing cloning and absolutely fell in love with it. And really, I didn't know what I was going to do when I graduated with a bachelor's degree in biology, which a lot of people don't. And I was offered an opportunity. We had the USDA ARS on campus, and they were looking to fund a graduate research project to look at the effect of nutrients on disease in plants. And that really is what I have been wanting to look at my whole life. I love going out and looking for disease in the landscape. And so it was a perfect opportunity there. And so Jonathan France was the USDA researcher at the time, and it seemed like a great fit. And so we looked at silicon and boron, and we really saw some amazing effects with silicon in Arabidopsis and in tobacco. And both of these plants in the literature were supposed to have no effect when it came to silicon. They were called low accumulators or non-accumulators. And the literature just seemed to be completely wrong. And it didn't make sense to me. And when things don't make sense to me, I just wanted to understand it more. And so I really dove down the rabbit's hole, and I have not come up since. I absolutely love everything that I've been learning about silicon, and there's so much to learn. And so there's a lot to do, and I probably will be in this career field the rest of my life looking into it.
Silicon and boron chemically are similar in some respects, are they not?
Yes. Yep. And they go to similar spots in the plant, but just like other nutrients, they have very specific functions that we're still learning about what they're doing at the actual cellular and molecular level.
Okay. Is silicon a nutrient or biostimulant? Or both?
Well, if we are talking about from a regulatory standpoint, silicon in the United States is considered a beneficial substance, which puts it in with the biostimulants. And so it is recognized in the US as a biostimulant or a beneficial substance. However, if we think of it from my perspective, in my opinion, it is a plant nutrient, and it is essential when we think of plant health. And so what happens is, as we're growing plants in a silicon-deprived environment, they're more susceptible to disease, they're more susceptible to stress. And that's why I consider it a plant nutrient. It doesn't meet what we know as the essential terms, which were made back in the late 40s, and so since it doesn't fit into that, people don't recognize it as an essential nutrient, but it definitely is a plant nutrient that's needed for a lot of different things. And that's what we're trying to understand, is how it works within the plant to help support and have the regulatory bodies see it as more than just a beneficial substance or biostimulant. I'm not hearing any audio right now.
It's because I muted everybody and myself. I wanted to make sure there wasn't any background noise. Yeah. So one of the joys of podcasting and learning to podcast is muting and unmuting. So yeah, I'm just going to say that, guys. If you're just listening, just go ahead and mute because we don't want any background noise. But what I was saying that you couldn't hear is, for the longest time, and you still see it in some of the articles, Wendy, is this classification of plants as accumulators, non-accumulators. Is that accurate? What explain a little bit more about how plants accumulate silicon, and does it really matter if a plant is quote unquote a low, mid, or high accumulator? What's that all about?
So this whole idea on low and high accumulator came from research that was done in Japan, and it actually started in the early 1900s. There was a German researcher, Strigel, who looked at plants that were grown on the same soil. So he looked at grass species and dicots. And what he found was the only two nutrients that were changing significantly was silicon and calcium. And so from that, he saw that the plants that had lower calcium had higher silicon, and the plants that had higher silicon had lower calcium. And so they were using that as an inference for whether a plant accumulated high or low amounts of silicon. And so they used the silicon and the calcium ratio to do that. However, when we look at silicon in the context of a nutrient, so if we look at it like how we look at nitrogen, how we look at phosphate, our macro and our micronutrients, we determine whether it's a macronutrient if a leaf tissue has higher than 1,000 parts per million that's present. So when we take what is called a high accumulator, they have to have at least 1% silicon in their tissue to be considered a high accumulator. At 1%, that's 10,000 parts per million. So this is up within the phosphate, the nitrogen, and even in grass species, it's as higher than the carbon. So it's significantly, so really what they're calling high accumulators in the literature, we can think of as hyperaccumulators. There are a few plants that take up a really high amount, and then the rest of them take up silicon within the levels of other nutrients. So looking at dicots, which a lot of times they say dicots don't need silicon as much as the monocots or the grass species. But what we actually see is in the majority of dicots, they take up silicon as a macronutrient. So they take up over 1,000 parts per million into their leaf tissue. And so when we start putting silicon back into that context of the nutrient, this is where we're trying to kind of re-educate and re-look at it, because that idea of the high and the low that has been used, and it's been very important for our understanding and getting us to this point with silicon, it doesn't fit into how we think of nutrients and how we think of fertilizers here in the US. So it kind of gives us an odd and maybe an unbiased or a biased perspective on whether plants are going to respond or have positive results when we start fertilizing with silicon.
So if a plant is a quote low accumulator, where it doesn't accumulate 100,000 parts per million like rice may, that doesn't mean that silicon is any less beneficial to those plants, right?
Correct. So when my favorite example is tomato. I've done a lot of work with tomato, mainly because in the literature, it's referred to as an excluder. It does not exclude silicon. It tightly regulates how much silicon this plant will take up. And so again, tomatoes take up silicon as a macronutrient. They take up over 1,000 parts per million into the tissue, and they have all sorts of positive responses that have been put out in the literature to salt stress, drought stress, heavy metal, disease suppression, when we start treating these plants with silicon. So what we have to remember is those plants that require such high amounts is because not only are they using it for those beneficial effects that we talk about as a biostimulant or a beneficial substance, but they also have structural needs for that. So they have processes called biosolidification. And we can think of that a lot, for instance, with us in our bones. If we looked at how much calcium was in an animal that has bones or in our vertebrates versus an invertebrate, so a human versus a worm, We need calcium for muscle movement, for neural function. But when we look at total volume or total concentration, humans are going to have a really, really high percent calcium compared to that worm, but it doesn't mean that it's any more or less important when we're looking at cellular functions and responses that are going on within the cell. It just means that we have additional uses for that. And so our application rates and the requirements for those high accumulators or hyperaccumulators are going to be higher than those for our other dicots and those that accumulate at the macronutrient level.
Okay. How about the absorption of silicon, using, say, tomato for an example? It's classified as an excluder, yet you just explained all the benefits that silicon provides tomatoes. What about how plants absorb silicon through active, passive, what pathways through the roots, foliar? How are plants taking up, and in what forms?
Yep. Wow, that is a very loaded question.
Yeah.
So
Make it one step at a time.
Okay, so let's first talk about the different forms of silicon, and then we'll kind of talk about how they move through the leaf or the plant tissue. So silicon, and we use the word silicon to talk about the element Si. Silicic acid is the, I like to think of it as a water soluble or the plant available. This is Si with 4 hydroxyl groups around it. This is the form that is the best well-known that's absorbed and used by the plants. And we'll get back to why I do not say that it is the only form of available silicon, because we are too naive in our understanding of what silicon is and how it's used to say that this is the only way plants can take up silicon. And then you have your silica, which is SiO2, and that can be in a glass and in other amorphous forms. So crystalline or amorphous, and I think I'm probably diving down too deep with that, but they're just different ways to describe silica. And then you have your silicates, which have a cation, whether it's calcium, potassium, or sodium. And so this gives us our calcium silicates, potassium silicates, or our sodium silicates. And then you can have even your silica nanostructures, or they're called a number of different things, where the silicon is the main component of the nanostructures. And all of these we know provide silicon to the plant and can provide the beneficial responses that we see. And so with that, we're still understanding how plants absorb silicon from the environment. We know there have been 2 transporters that have been identified that transport the silicic acid molecule. And these are both through passive, which means it just moves down a concentration gradient, and through active transport, which means the plant actually needs to use energy to get that to move opposite the concentration gradient. But when we talk about these transporters, they're still all regulated within the plant. So they can move these transporters into and out of the membranes to change how much silicon that they're taking up during any certain time in the plant growth. So with these 2 transporters that I discussed, these have been found in the root tissue and also expressed in the nodes, or the parts where the leaves attach to the stems on the different plants. And so this is where silicon can be absorbed through the roots, move up through the xylem. So another thing, silicic acid does not move into the phloem. So this is a xylem movement with that. So it follows the transpiration stream and then can be distributed into new growing tissue, whether that's up into the new growing leaves or down into the expanding root system. But we do know that when you apply silicon foliarly, you still get a response and they still see silicon moving into the leaf. And this, like other nutrients, silicon does have pathways that are likely for this to happen. We don't know exactly how it's moving in. It's not likely through those 2 transporters that were identified within the root system. But there are other mechanisms. It can move in likely through hydrothodes as it goes in through the water. It can also, since it's a neutral compound, migrate through the cuticle and get to the epidermal layer. And then if there's transport mechanisms to move further in. But when we think of the larger, so a lot of the research looks specifically at silicic acid, but we know that plants and cells can absorb larger molecules through endocytosis. So this is where the membrane kind of just swallows what's out surrounding it. And this is likely how we're getting accumulation and movement of the larger particles like the nanosilica particles, or even polymers. So the silicic acid, if there's grouping together in shorter or slightly longer chains, we still could get movement of those forms of silicon into the plant. But again, they're not really studied at all, and there's not a lot of literature on those, and it's mainly focused on the silicic acid.
And I do want to back up because you mentioned two different types of silicon, and we are all about diving down the rabbit hole. So,
okay,
because when it comes to silica, that word, there's also another one that people may have heard of, silicosis, right? Silicon in some forms can be hazardous, and that, my understanding is it's mainly the crystalline forms, but amorphous, which I'll let you explain what amorphous silica is non-hazardous, right? There's safe and maybe unsafe forms of silica, and what are those differences? And that does go back to crystalline versus amorphous, right?
Correct. Yep. So with that, what you're referring to is when you develop mesothelioma or ciliosis of the lungs. So what happens with those particles that are dangerous, they're actually, so the crystalline form, you can think of like an ice cube, where it's very well structured. And the amorphous is more kind of like a gel or a jello. And so when you get these structured sizes, and they're usually less than 5 microns, that is a really, really important size fraction, because particles that are under that 5 microns, we can inhale deeper into our lung tissue. And so what happens is we inhale those small silicate particles. With them being crystalline, our bodies can't break them down. And so we have these immune cells called macrophages that actually come in and try to engulf and break down these particles. And this is one idea of what's happening that causes the disease progression. The other interesting thing, silicon is important for animal health as well as it is for plant health. And so what they think might also be happening is that we can get a certain size cells called fibroblasts that can colonize these silica particles, and they put out these extracellular matrix, which actually builds up scar tissue within the lungs, and that might also be playing a role in the disease progression. So this, we're talking about less than 5 microns of a crystalline type silicate is going to cause those health issues. When we look at the products that are on the market as silicon fertilizers, these tend to be larger particles in an amorphous, because as they're in more of that gel or less structured, they're more easily broken apart by enzymes, by weathering processes that release that silicic acid. And those silicic acid molecules, we believe, are what's important to have the immune response, the defense response that we see at the cellular level. And that's why those are not likely to be inhaled as deeply into the lungs, and then they're easily broken down compared to the crystalline, to where they don't have that same health risk as your fumed silica and certain products that are mined silica products can have those crystalline and that particle size.
Got it. Yeah, I'm glad we backed up to that.
Question.
Thank you.
I used to own a hydro store, and one of the things that they tried to sell me every 2 years was a new brand with some sort of an inert medium, usually some form of a rock that was silica based or had 20,000 parts per million silica and, a million different micronutrients. Are those in the realm of the dangerous types of silica?
It is really, really hard to see. I have worked with also diatomaceous earth products. It is not clear from the labeling or even some of the SDS on what their particle size is. So it's hard to tell unless your manufacturer, who you're buying it from, is well versed in how it was manufactured. I can't say whether it would be or not. For the most part, a lot of the products, the particle size is too large, and it tends to be sand. Even if it's quartz sand, they're larger particle size that you don't have to worry about that. It's when you get into the powdered or the fumed type of products that you really need to be well aware of how they were processed and what their size distribution are on the lower end.
Okay.
Wendy, I also want to back up, since we're starting to talk about products and plant absorption. And I don't think we covered this earlier about the availability of silicon in the soil. I mean, it is the second most abundant element in the soil, and I believe the eighth most abundant in all of the universe, yet it's not readily available. Is that correct?
Well, it has a low solubility in solution. And so what that means is, yes, there's a lot of silicon out there, but it's not all in the silicic acid form, and it's not all in the amorphous form. So we still have, especially, we're looking at sand. Sand is going to be a crystalline form, and it takes microbial weathering and other weathering processes to get that down and to start to release the silicic acid from that. Clay material is more likely to release it, but again, the solubility of silicon in solution is really, the higher end is about 2 millimolar or 60 parts per million of silicon. And in a soil solution, we typically see much less than that. And that's because if you think about it, every cell requires silicon. And so you have a lot of microbes, you have plant roots, you have worms, you have so many things within any environment, whether it's a water environment, a soil environment, that's all competing for that silicon source. And then when we get into these heavily agriculture areas where we pulled silicon out and we have not been putting it in, what we do is we deplete that dissolved silica pool or that available silica pool, and we haven't replenished that. And so now we're waiting on these processes that usually take a long amount of time to break down those soil parent materials to release the silicic acid, because we're not returning a lot of the crop debris or the leaf material back to the field to where it would naturally work back in. And so that's one of the reasons why we're seeing such great responses to silicon fertilization, especially on either higher weathered soils or in heavily cropped areas where it hasn't been applied.
Right. So when we create a monoculture situation, we exacerbate the issue of removing the silicon. I'm glad you said that every cell requires silicon.
Yeah.
And it's another reminder that once you go below the soil surface, there are a lot of organisms residing there if you have a healthy soil. And then so I'm wondering then, if silicon is being depleted and not then readily resolubilized, silicon then would also impact soil health.
Yes, and that's something I know Brenda Tabana is doing a lot of work at LSU looking at silicon in soils, and there are other research around the U.S. and different countries, but I don't know many looking at actual soil health, because when we think of silicon, it's going to be a big limiting factor in what the microbial community and what that soil looks like. And so, the problem is we all look to see what's high in the soil or the waterways, but really what we also need to be looking for is what's missing, what's limiting us in that. And so what role silicon plays on microbial community in the soils with microbial health, that also could be a really big area of research that we we need to get into, or we need some people to kind of start looking into or making that part of what they're already doing with all of the microbial biomes and rhizomes that they've been doing out there.
Yeah, I don't see a lot of crop consultants recommending silicon analysis as part of the annual or biannual recommendations. And even testing silicon is kind of a challenge, is it not?
Yes. Yep. And just like any other nutrient, the value is only as good as the extraction. And then different labs are going to have slightly different values from that method. So that's when you find a lab that you want to work with, you want to stay with that lab because you're going to have consistent responses that might be different than another lab, but you know what that means in response to yield, in response to your outcomes with that. And so that's the same with these different test methods that we have for silicon. There is no best method, but we can use the information from these extractions to give us an idea of what to expect. Whether we are deficient in the soils, whether a product is releasing the amount of salicylic acid that we need for that, or sorry, I just lost my train of thought.
No, that's okay. I'll prompt, since you lost your train of thought. So having consistent laboratory testing is important. However, and I'm speaking from personal experience here because I think of a mistake that was made and then there's differences on soil testing for silicon and tissue testing. And it's important to have, when you do tissue testing, that the silicon is digested using an alkaline extraction, right? Versus acid. And acid is more common with other nutrients, the other macro and micronutrients. Is that correct or incorrect? And if either way, correct me if I'm wrong or elaborate on that.
That is correct. This is one issue that we have, why it's really hard to get silicon analysis in plant tissue here in the US. So your nutrient analysis on plant tissue is an acid digest, and they can give you every element, including silicon. And there are some labs that used to give the silicon line. The problem is when you put silicon in an acid, it polymerizes. And before they run the analysis on their ICP or even colorimetrically, they filter out the solution. And so that silicon that's in your tissue is actually left behind on the filter. And so typically we'll see silicon values in plant tissue ranging anywhere from 10 to 20 parts per million up to 300 or 500 parts per million in plant tissue that should be at 10,000 parts per million or higher. And so it either they do a separate digest where they use an alkaline like a sodium hydroxide or a potassium hydroxide, or they can also use hydrofluoric acid. So HF was used in the past a lot. People get away from it because of the dangers of working with it in the lab. But that fluoride actually helps keep that silicon in solution. And so if an acid digest is being performed and HF is part of that digestion, then the silicon values in that extraction are likely to be accurate.
Gotcha. And that's exactly what happened to us. We ran a trial on, I think, a dicot and a monocot, two model species, zinnia, and then I think the dark horse variety of grass. I can't remember what poet?
Borealis.
Yes. And we were expecting, a couple thousand or more parts per million. And we sent the tests off and the lab said, yeah, we test for silicon. Awesome. Get the lab results back. No more than 100 parts per million. Wait a second. And then they started to backtrack like, oh, darn it. And didn't do it the right way. And so fortunately, I think that's one thing that anyone supplementing their crop or soil with silicon, if they're going to test, which I think we all here advocate for testing, is because you can't manage what you don't measure, is to make sure that you clarify that with the lab that you're using. How are you extracting that silicon? And if they say, well, we use an acid extraction, say, oh, okay, we'll back up. Maybe provide them. If they don't do it that way, you probably need to look at a different lab because your lab results could be really low and essentially then erroneous.
Correct. Correct. It's not even worth paying to have that analysis done.
Right.
Yep.
Now, I think we need to maybe even back up again because we've talked about silicon in the soil and then testing for it. But there's a litany of things that silicon does for plants, both physically and chemically. And there's a lot of different benefits. I'm finding more. Most people hear abiotic stress relief, but there's a whole bunch more benefits that silicon provides. Can you share some of those with us? Maybe some of your research or what you found in the literature here recently?
Definitely. So the reason that we hear a lot on abiotic stress and not really a lot on other things is because as companies are educating you on the products, as a fertilizer, we can only educate on what abiotic response is. When we start talking about disease suppression, when we start talking about how it increases growth, these now bring it into the realm of possibly being a pesticide or a plant growth regulator, a PGR. And so these aspects of silicon aren't really talked a lot about by companies. However, again, silicon is a nutrient, just like nitrogen. If we never fed nitrogen to the plants and then all of a sudden we started giving nitrogen and we're like, oh my gosh, the plant's getting bigger, it's growing better, it's greener, it's not as susceptible to powdery mildew and disease. Oh, does that make nitrogen a PGR or a pesticide? The answer is no. We know it's a nutrient. We know the effect is coming because the plant needs that nutrition. This is the same thing with silicon. So silicon actually works and we don't know exactly. So there's a lot of studies right now that's looking at how it is involved in water relations. We know when we start feeding with silicon, the transpiration for the most part seems to reduce, but it doesn't always go down. What it does is it balances. Silicon, when we start giving it to that, we'll see other nutrients like phosphate and nitrogen use efficiency goes up. And that's because the plant isn't taking up as much of these nutrients because now it has silicon. So as plants are deprived of silicon, they're scavenging and they're just trying to pull everything up that they can to try and get that silicon to fit that need of the plant. So think of it when you're really, really hungry and you're craving a food, but you don't have that food in your house, you tend to overeat everything else, just trying to get what it is that you're craving. So when we start putting silicon back in, we have a better nutrient balance within the plant. We have a better water balance. And that alone is going to make a healthier plant. So if you think about it, when you're not feeling well, when you're sick, they tell you to make sure that you're hydrated. When you're trying to stay healthy, work out, they tell you to stay hydrated. Water is really, really important to make sure that the nutrients are going where they need to, the toxins are coming out. And it's really that whole balanced idea. And so when we think of silicon, the responses that you see, especially if the plants or the system is deprived of silicon, you're going to see a reduction to disease. And when I say disease, I talk about both abiotic and biotic, but fungal diseases, so your mildews, your rots, all of these, the plant is going to respond better. And silicon isn't directly killing the pathogen. It's allowing the plant to respond more rapidly and have a better immune response to that. And so we see a lot of the enzymes that are involved in defense they respond better and they're more active when we have silicon present than when we don't. So again, not a pesticide because it's not directly affecting the pathogen. We see, sorry, I'm trying to think of non-abiotic. So really with the pathogens, viral infections, bacterial infections, and fungal infections, silicon helps those plants respond better to all of those. And then with the growth, it helps enhance root growth. It helps enhance foliage growth. And again, this is when the plants are truly deprived of it in their system. And it's not working as a plant growth regulator. What it's doing again is it's giving a better nutrient balance, better water balance, which is allowing the plant to take advantage of its growing environment better than if it didn't have it there. And so these differences in growth and in disease tolerance is due to what's happening internally within the plant.
Very cool. I feel I have a lot of questions, but I know this is a shared podcast. Do my co-hosts have anything they want to chime in on at the moment?
Yeah, I'll jump in. Can you hear me okay?
Loud and clear.
Wendy, it's really good to see you again. A year or 6 months ago, I asked you a question about what we were seeing in plants with an amorphous type nanostructured silica foliarly applied. And I asked you then, does it have a pathway to benefit the plant? And you said, absolutely. We don't know exactly how, or but you've explained a lot already. But explain to me, with a vineyard grower who applied this product, an amorphous foliar, he saw a tremendous plant response in overall plant health, canopy growth in the grapes, and fruit quality. Can you maybe, you mentioned a lot of things, but could you explain a little bit about why we saw that?
Definitely. And again, this is all, the research is not, it's lacking because it's new. We're starting to understand it as a nutrient now, and I'm hoping that we'll get better research moving into it. But if we think about what might be going on, we know, and I say we know, but we have some preliminary data that show when we spray a leaf with water, we get a response. We get silicon moving up into the plant. And so when we start applying these products foliarly, we think of it just being the product, but we don't think of the whole system and what's going on. So not only are you likely getting the response coming in from that material on the leaf, possibly getting into the leaf, and they have studies on nanoparticles where they show the particles moving into the leaf tissue when foliar applied. And then they also see an increase in the silicic acid or the silicon that's in that leaf tissue that they believe is, as those particles break down within that environment, it's releasing silicic acid from the outer surface of those materials. But you also get that added benefit that if you do have silicon dissolved silicic acid in the soil system, you're going to get additional uptake. So it's like you're getting it from both sections that I think we haven't really looked a lot in the research on what effect that has. And so this is why in the field studies, when you start putting it out, again, you tend to see, especially in vineyards, which, they've been growing for quite some time on that same soil without putting the silicon back in. The silicon that has been taken up in the dissolved form is being sequestered in the root system, in the vines, and depending on how they treat the leaf litter, that might be getting back into the system, or it might completely be tied up or removed from the system. And so you're depriving it there of that. And so with these particles, it's probably that double hit that you get it coming in through the leaf and also up through the root system, that's giving it the benefit to where it's all throughout. Because again, with silicon not being able, or silicic acid doesn't move through the phloem, we still see responses in roots and leaves of foliar applied silicon, and it's likely due to triggering a mechanism that we really don't understand yet what that is.
Thanks, Wendy.
You're welcome.
So Wendy, if someone's going to add silicon, and I should also back up that we're covering, our listeners are growers from across the spectrum, field, greenhouse, so therefore we're dealing with soilless media. And I think we've established that all plants benefit from silicon. How much? as we know, that some of them take up less, others take up way more. They benefit equally. What types of rates should growers be considering? I know the answer, but I'm not going to say it because I want you to explain kind of why. And then, like how often are some systems? I would guess that soilless systems are more devoid of silicon than mineral soil, since we've talked about how much is potentially available in the soil. But can you walk us through, like, rates and frequencies and the different systems? Pick and choose what you want to answer from that. I know that was another long list of things.
Okay, so I did do a 4-year postdoc with the USDA ARS. Jonathan brought me on, so I did get into horticulture and floriculture through that group. And I can talk on hydroponics and soilless because a lot of our research, we used a deep water hydroponic system because we could get clean roots. So a lot of my research is in hydroponics, just because it's easier to do cellular and molecular stuff when you don't have dirty roots to pull from. So with that, rates, I have always recommended 30 to 60 parts per million. This is in the range of 1 to 2 millimolar. And I'm sorry, I should have had a whole list of my conversion factors, but we'll stick with millimolar and ppm right now. Why those are important? Again, when we think of the solubility limit of silicon in solution, that's at about 2.7 millimolar, or just above that 60 ppm mark. And so the absorption capacity of roots have evolved with that solubility of silicon in the soil solution. Putting higher amounts in, when we think about fertigation in soilless media, I'll get back to recycled systems, nutrient systems here in a minute, like your NFT systems. But when we're fertigating to pour through runoff, sorry, I'm getting my terms mixed up.
Drain to waste.
Thank you. Yes. That's where that 30 to 60 ppm, we know we're going to give enough for those roots to absorb, but we're not going to overfeed it to where we're just pouring it down the drain. When we get into the NFT system, we're recycling that nutrient solution through, again, depending on the formulation of silicon that you're putting in there. Some of these products you can put in at a higher rate than that 60 ppm solubility, so you can get a higher bump in there. And so with a recycled system, unless you want to be adding it back in every few days or weeklies, those systems you can apply at a higher rate, again, because they're going to be continually pulling that silicon out. And I haven't really sat down and thought about what rate I would recommend for those systems. And maybe that's a follow-up answer that I can give to you at a later date. But those, again, you would just think about, if you're going to do 30 or 60 ppm a week, how many weeks are you going to have them in that system and do that kind of, and that'll get you close. The great thing about silicon that I'll bring up here, you cannot over-fertilize with silicon. You will not get toxicity. You will not get leaf burn. And again, going back to me saying that tomatoes are not excluders, they are regulators. Plants have evolved around silicon. And so they tightly regulate silicon. I would almost argue more so than any other nutrient that's out there in plant tissue. And they do so, I think, because it is very important for enzymatic activity and certain processes that go on in the leaf that we're not going to talk about because it gets really cellular molecularly, and we'll try to kind of pull back from that. But you can put too much silicon in a system and not have to worry about whether your plants are macroaccumulators or microaccumulators. They're not going to care if there's too much silicon. The only asterisk I put on that, when you start to get above 1,000 parts per million at these really, really ridiculously high ranges in like an NFT system, if you have a low concentration of your metals like zinc or nickel, You might have the silicon tie those nutrients up, and you might induce a metal deficiency. But this is only when we're putting in really, really high concentrations of that, and you have really, really low concentrations of those essential metals that the plant needs. But other than that, those would be my recommendation rates in hydroponic systems. And these are for the liquid. When we get into the solids, like the calcium silicate products and some of the other solid products that are out on the market, those you're going to put at a higher rate because those are going to break down over time and release the silicic acid. So those depend a lot on what the material is and how much of that is going to be released as silicic acid. So those are harder to say. But with the liquids, 30 to 60 ppm is definitely my target range.
And that's 30 to 60 ppms of the element silicon.
Silicic acid, yes. So percent SI, which means the amount of silicic acid, not the total amount of silicon that's in the product. So a lot of these products can have high amounts of silicon, but again, they're in more of those amorphous, so they're tied up, and they may release that silicic acid over time, but that's 60 to ppm of that silicic acid in the SI that's coming off, correct?
So let me clarify that then, because monosilicic acid is what percent silicon?
So yes, so monosilicic acid, sorry, let me kind of regroup here. On labels, depending on what state you're in and how they allow these products to be labeled, you might see a percent SI, a percent SiO2, or a percent SiOH4. These are all based on a test method that told them how much percent SI is there. And then they use a conversion factor to get to those other two compounds. So really easily thinking, and correct me if I'm wrong because I might do these numbers, I don't have the numbers in front of me. To go from percent SI to SiO2, you multiply by almost 2. And to go from SiO2 to SiO4, you multiply by about 4. So if you have a 1% silicon, that's synonymous to if they say you have a 2% silica or a 4% silicic acid. So those numbers all mean the same thing. So at that point, having a 4% silicic acid or a 2% SI, your 2% SI is actually going to have a higher amount of the plant available silicon compared to that 4% silicic acid label.
So but then again, is it similar then, Wendy, to whether you're applying phosphorus or phosphate?
Yes.
Is that how you're looking at it? Because I thought and please, again, correct me, through some of the research that you've done, I thought the application, the rate was of 1 to 2 millimolar of Si, the element, and which is a percentage of the monosilicic acid. Drilling down, so that way you're segregating it, saying, okay, we're dealing with silicon, we're not dealing with the H4SiO4 or SiO2. We're really getting into how much of the element we're providing, similar to if I need so much phosphorus and I'm given phosphate, then I know, okay, I need, 33%, 37%, something like that. I always get potash and phosphate mixed up.
Right. And yes, you're thinking of it, but yeah, it is percent SI is that 1 to 2 millimolar, 30 to 60 ppm, not SiOH4.
Okay, great.
Yep.
Awesome.
I had a question. Like I said earlier, I owned a hydro store, and years and years ago, an orchid farmer came in and turned me on my first potassium silica product. And I sold that and many different versions of it for years and years. And, as of recently, there's been a lot of these new products that have monosilicic acid in it, and they seem to work very well, very similarly, but the price point on them seems to be incredibly higher than, I used to sell a bottle of silica for between, $10 and $20 for a liter. Some of the stuff I'm seeing online is anywhere from, almost $100 for 500 mils. Is there any justification for this price? Is it that rare of an element, or is this, marketed to a specific crowd that's just willing to pay, in your opinion?
Oh, this is going to get me into so much trouble.
I love it.
I
Uh-oh.
honestly think it is marketed to a specific crowd that will pay that price point because what they're getting out of it is a high commodity crop in certain areas of the U.S. that Ohio is not a part of. But with that, it really there are a number of things that go into it. Some of these products that are manufactured have high input costs. So there are different manufacturing processes for the products to where that could be incorporated into the higher costs. A lot of the products that you're talking about that are at the really, really high end, I have no clue what's in them. I've read through SDS, I've read labels. I don't know what you're buying to recommend some of these products as to why they would, what it is that you're getting for that price. Not that they aren't as so. It's normally it's for certain markets, and they're labeled for that market, and that's where those costs likely come from.
Okay.
So that's all economically driven, I from my opinion, and I am more of a scientist than an economist, and so
Thank you.
we'll leave it
Yeah,
at that.
I get asked that all the time.
Okay.
We could stay on that for a moment because Wendy,
Oh, no.
you're involved in organizations that deal with labeling. Can you help consumers understand the confusion that exists on labels? Because silicon, when it comes to labeling, can get kind of confusing because and this goes across the board for other things as well, the non-standardization of labeling. So how do consumers begin to understand what they're buying when they pick up and look at a label?
Right. And it is confusing. I'm confused almost every time that I see a new label. But one great thing, so I am an industry liaison with APCO, which is the American Association of Plant Food Control Officials. They are doing an amazing job trying to get everything labeled into one label format for all 50 states is their goal. And they've been working really, really hard to try and come at this, especially since a lot of the biostimulants now are going to fall under the regulation by this group. With that, though, and again, I'm new to this organization, so I'm just learning all of this. How labels are actually done in the US is it's a state by state determination on what they're going to allow on that label, what they want it to say, what they want it to look like. APCO has a recommendation, and what they do is they all get together a couple times a year or a few more and come up with how they all agree to what the best way is to label and make it easier for the consumers. Not all the state, and as a state, they do not have to accept what APCO decides, but it gives guidance on how an appropriate way to do this. One of the problems with silicon is it's still new. Even though APCO has recognized it for quite a few years now, they're still trying to understand what exactly it is. And that's why silicon and these biostimulant products, as they're coming out onto the market, the labeling is going to be confusing as states try to understand what the best way to label them is. And that's why right now we do see percent SI, we do see percent SiO2. I don't think we're seeing it as much. They used to list total silicon on the label, which is completely meaningless. Total silicon tells the consumer nothing. So right now, how APCO has suggested for labeling, the silicon that's on the label should be the plant available or the silicic acid amount of silicon that's in that product. And again, whether it's Si, SiO2, or SiOH4, you're really looking for that percent silicon to be above a certain number. And so labeling is going to be, I think, an issue for the next few years, but they're really working hard to make sure that there is a unified front to make it easier. So it's a lot better, I have to say, than it was when I started as a graduate student, looking at silicon and looking at all of these, trying to figure out what the heck was out there. But it still has quite a way to go.
Yeah, that's one of the frustrations that I'm not sure that consumers are aware from a manufacturing standpoint is in the United States. It's kind of like Baskin Robbins. There's 31 different flavors. We've got 50 different possibilities for labels. So it kind of puts a burden on companies when they have to follow different, have different labels for different states. And it sure would be nice if we can, and we appreciate the work that you and all the other liaisons and even those at the state level. I'm sure if we could standardize it, it'd be a more perfect world, but
well,
so
and
keep up the
Yes,
work.
it would.
Yeah, they are doing that. And honestly, California, Washington, and Oregon, they're doing a great job trying to get that standardized. And they've done a lot of concessions. They are doing an amazing job as state regulators trying, and they do see that this is a big issue. And this group that's in AFCO right now and running that organization they're doing their best, and really they're doing an amazing job. So give them, it's taking some time because some states do have to change laws to actually change how labels are allowed. So it will take time, but it is getting better. And so I am very optimistic that it will get better as time goes on.
Yeah, I'm with you. I'm optimistic as well, and I think this is another call for the manufacturers listening to this podcast. Is just like biostimulants, we need to really continue that effort of the market's big enough for all of us. Let's just make sure we're all playing, so we can weed out those that are the nefarious ones. Those that are really making the snake oils, because that's one of the things that's limiting the adoption of biostimulants and silicon to a lot of consumers. They consider it a biostimulant. Hopefully from this, our conversation, they'll understand that no, it's a nutrient, and we will view it as such. Because as you mentioned earlier, you were talking about different things being biostimulants. Well, shoot, according to the EPA, water could be a PGR, depending on how it's used. If you're starving and you add water, yeah, you're regulating the growth of the plant. And we deal with that in other associations as well. It's because, BioAg manufactures humic substances, and we start getting into humic and fulvic, we deal with some of the same issues on labeling. So those out there fighting the good fight, like yourself, Wendy, keep it up. We appreciate what you do as a liaison. And yeah, just keep it up.
I'm Nathan. I work for Shango. I'm a lead cultivator here in Oregon State. I met Josh about a year ago. He works for BioAg, and he's given me a lot of samples to test out, and every single product I've ever used has by far gone above and beyond what I've ever expected. So Ion 14, using that in a root drench, I started taking data on individual plants from about 15 different genetics, and what I noticed was my node spacing got cut in half, and my stacking going into flower increased by about 10 to 12%. When using my BioSupersil in veg and moving to about day 10 of flower, I got an increase of about 10 to 15% in my growth of height overall between every single genetic that I had in my building. I have not had one plant actually that has not liked it. Every single plant, whether it was a short stout indica or a tall lengthy sativa, every single plant has adjusted to it and taken to it in such a way that I will not have that in my garden. Any given point in time, I will have anywhere from about 9 minimum and a max of about 20 different genetics in a building. Oh, it was beyond easy. I slowly integrated it at first, did a few test plants in both my veg rooms upstairs and downstairs. I did some with bigger, older moms that I had that were, in 7-gallon pots, some that were in 3-gallon pots, see what difference they would have and different genetics. Every single one loved it. So I decided, okay, I'm going to start doing whole benches in my veggies. One would get just Ion 14, one would just get Bio Supersil, one would get Cyto Plus, and see the differences. And then I combined them all together with the feed ratio that I give them. And I was able to increase my food by about 10% and they not skip a beat. On top of that, I get my plants in within 30 days now can go from a rock wool cube to a 2-gal and back into my flower room and not skip one beat.
I do have one other question here, and there are going to be a couple of questions that kind of start to deviate from silicon. So I want to give my colleagues here an opportunity to ask any other questions, because I think there's some things that they want to ask. Otherwise, I'm going to keep rolling.
Oh, I got my big one answered.
I have many more, Wendy, but I will hold them.
Okay.
So let's talk about nuts and bolts on the farm for a minute. So I've got growers that are really interested in, abiotic stress, biotic stress, fungal infections, plant health stuff. What's the first step for a grower to really analyze where he's at with silica in his crop? And then what would you suggest would be the best application to amend that?
That's a great question. And it's one that I get asked a lot that I always come back with. When you're trying to assess what the needs of silicon are for that plant, with our understanding of silicon at the moment where it is, my best recommendations are to put it out there and see what responses you get. And I know, that's not the best answer, but our test methods and how we test for deficiency have not yet been well defined within high accumulating crops. So when we start getting into these vineyards, into orchards, and into other arenas where we don't have as much data as we do on the hyperaccumulators, it's really hard to come up with what's that special number that you need to see that tells you, I need to start adding silicon in. So at those, you can look, you can do a tissue analysis. And if you have data from that crop, that specific crop, like for instance, grape, I believe, take up about 4,000 parts per million or 0.4% silicon. If you're growing grapes and you're at about 500 ppm or 1,000 ppm, those grapes might greatly benefit from the addition of that. At the same time, with silicon not having a negative effect when it's not needed, going out and applying it to the system and seeing if you get that response that you are wanting to see is the best way, if you can afford it and you can do that to a small area, that I like to recommend. At that, however, if you do start to apply it and you see these wonderful responses, what that tells me and triggers me is that you are very, very deficient in the soil or in the growing system, whether it's soil, soilless media. And so one way, if you're not in a greenhouse or a production group and you're in soils, not only do you want to use products like liquid products or foliar products that are going to get that crop there, you need to think about how you're going to start rebuilding that soil health and those soil levels. And so that's when you want to come in with products that are going to have a longer residual time in the soil and that will break down over time, knowing that you're still going to see great benefits coming in with those foliars, just like you would with any other foliar nutrient that you're coming in and taking care of a situation. It's treating the symptoms, not really correcting for the complete problem. So those would be, those are the suggestions that I give out, but really understanding what a silicon deficiency is in the wide range of plants that we grow here in the US for production. We're not close to having those yet, at least not that I've seen in the literature.
And so go ahead, Bill.
Thank you. I just wanted to say thanks, Wendy.
So then that also goes back to building along those lines, field production. There's another reason to build healthy soil and focus on making sure you're monitoring, measuring soil health. And that means a healthy microbial balance in the soil, because some of those microbes are silicate solubilizing bacteria as well, are they not?
Correct. Yes.
Yeah.
So you have
go ahead. I'm sorry. Go ahead.
No. There are quite a few that do that. Yes.
Yeah. So you could be supplementing silicon at the same time. You could be focused on building that soil health and let the microbes do some of that work for you, and still supplement via foliar or through the soil, especially maybe on those occasions where you're expecting some abiotic stress, just like we do when we monitor for other pathogens. Say, oh, I know my conditions are ripe for powdery mildew. Maybe I can help bulk this plant up. Or, hey, the weather forecaster is calling for extreme heat next week, like Oregon last year. I live in Arizona. It gets to 115. We don't break a sweat. You get to 115 in Oregon, the whole state's burning, right? And so,
absolutely.
Yes. So definitely those are the time. And that's when having a liquid product or a product that's more readily available than the slower releasing, which is going to give you a constant release, you're going to have a big surge or a big uptake from the plant under those stressful times. And so having that pool there that's available and ready when the plant needs it is why we see the responses that we do with both the abiotic and biotic stress when we're applying it. So applying it, another thing, prior to or during, right at the onset of the stress, is when you want to apply silicon. If you apply after the stress is there, just like most of your other treatments or nutrients, it's not going to correct the issue. And it's not like a pesticide where it's going to completely take you down to zero. It is just going to allow that plant to respond better. So if you have that extreme heat that Oregon had, no plant's going to make it through that. But the silicon treated plants are probably going to survive it longer. They're just not going to make it out the other end, because it's not going to protect against the extremities, but it is going to protect against your every day-to-day stress that's coming through.
Thank you. You just answered my next question.
Okay.
So silicon, use it as a prophylactic.
Yes.
There you go.
Use it as a nutrient.
Yes, as a nutrient. Yep. Excuse me. Nutrient. Come on. Silicon, nutrient.
But you can think of it just like you do any other nutrient. Deficiency, how do you get it in? So that's the big thing, is we've always put it on this weird pedestal or back here in this corner. It's this weird thing that just floats around. But no, it's a nutrient. It's an element just like our other nutrients. So when we start thinking of it, it makes more sense on how we should deal with it, what questions we should ask, what should we look at, those types of things.
My view, and it's my opinion, is I look at silicon as a nutrient similar to how I look at, and a plant's relation to it, similar to how I look at humic substances. Plants evolved with humics as they were evolving and under this extreme evolutionary stress to increase their absorption capacity, and things are dying. That ties into plants' relations to humic substances and the benefits we see. And that's why when we add them, and we at BioAg, we consider them essential, right? But you could argue one way or the other. But silicon, on the other hand, it's a no-brainer to me. That's an element that is so high in abundance that even though the solubility and availability of it is regulated and it's not readily available, it only makes sense to me that plants benefit from that. They evolved with it in the system. It may have been at a slow release or low levels, but no less important. And then, of course, we come in with the green revolution and mechanized agriculture, and now we're mining that soil. Silicon is just another one of those pieces, just like organic matter and microbial populations and the balance with bacteria and fungi and protozoa and all the other things. When it comes to field mineral soil, silicon is a major part of that. We need to be applying it. We need to be testing for it. Researchers like yourselves are establishing those levels. Okay, I grow rice, how much do I need? I grow corn, how much silicon do I need? I have hops, potatoes, etc. Speaking of hops and potatoes, you have also started your own company and are doing some research at your facilities, your home farm, right? What are some of the things you are looking at starting this season and beyond? What are some of the things you're doing?
Well, my background is cellular and molecular biology, so I'm really interested on how silicon is playing a role in water relations and different cell types within a plant. The one cells that I'm really interested in is looking at cork cells, or the part that makes up, when we think of the trunk of the tree, the bark, but also these cells are important in the skins of fruit. So, and different tubers. So potato is a great example of that. So this year I will be looking into growing potatoes and understanding how silicon is involved in those cell formations, because what that does is those cells help regulate how much water is lost through the skin or through the bark, because we don't think of wood, at least I never really thought of wood breathing, but we have a lot of transpiration that goes through the woods, through the branches. So it's not just the leaves that are moving the carbon dioxide and oxygen, it's the entire, all these different parts of the plants are involved in that. And so by looking at the potato, I hope to help understand why we see such great responses when we get into the vineyards, when we get into the orchards, in these dicot species, and how it's involved in water relationships within specifically those types of cells. And then the other thing that I found really important, if you try to find studies on silicon and hops, there's not a lot of studies in it. We know hops take up a really high amount, and it's actually the hops that are present in the IPAs or certain beers that give beer such a high silicon concentration, which again, silicon's important for the health of all animals. So drinking beer actually helps us get those silicon levels up to help maintain our healthy responses to that. But that's another species of plant that they talk about the benefits of the silicon in that plant tissue a lot, but I don't see a lot of research on where it's deposited throughout the plant, what effect it has on the plant health itself, with not thinking about the human or the animal side of things. And so potatoes and hops are going to be my two new entries into the gardens this year. Along with a few others that are present that we'll continue to look. And then we'll probably start looking at different types of silicon fertilizers, just kind of playing around and seeing where we can go with things.
Wendy, that's really interesting because I've got a grower up north here in the Silverton area that is very interested in using silica this season. So maybe I could ask you about what should we try and look at with him? He really wants to look at his cone quality and, terpenes, and because they really do get paid for quality hops, and that his yields are good. He needs to move into the quality zone, and so he's going to try some products. What would you suggest we do with him?
Oh, so off the top of my head, since I've never, and we're talking about hops, correct? Not potatoes. Just kidding. But I have not worked with hops. So, and the great thing with silicon is it doesn't tend to increase yield unless you're under like a massive silicon deficiency, but it's the quality of the crop that enhances when silicon's around. And what I tell people is, whatever the genetic potential of that strain or that species, that variety that you're using, those are the qualities that you want to look. So taking it, and again, I don't have a lot of work with grapes, but with talking with growers, there's the sweet grapes versus the non-sweet grapes. with the sweet grapes, you do see an increase in bricks. And there was a grower that was really concerned because he didn't want his bricks to increase. And I can't tell you what type of grape he was growing, but that was a big turnoff. He's like, why would I put silicon down? And he went ahead and used it. And what he saw is those grapes, actually the bricks went down in the grapes that he was growing. And again, this is because silicon isn't directly affecting the bricks. Silicon is bringing the plant into balance. Silicon is balancing out the nutrients, balancing out the enzymes, making the plant respond better. So if you have a plant that was bred to have these attributes, you're not going to get it to have the same attributes of a different one. So it's kind of like if you have a golfer and the golfer eats very healthy and you give the golfer all the food that they need in the healthy proportions, they're going to be the best golfer that they're going to be. But you can't take that golfer and expect him out on the football field, and vice versa. If you feed a linebacker, they're not going to swap spots, but they're already genetically the best for those particular scenarios, and they're going to perform at their best level. And so that's when we get it into plants. I would recommend just the quality traits that you would look for because we all pick varieties for a very specific reason. We want something specific from that variety. Those would be the traits that I would look for. And again, that's why I don't like to say that when you feed silicon to plants, it reduces transpiration, because sometimes the plants need to transpire to get through a stress or to move nutrients where they need to go. And we do see that sometimes transpiration does go up with silicon treatment, but it goes up because the plant needs it. That makes the plant healthier to transpire in that moment that it was measured. So it's not a higher or a lower, but it's getting that plant to its genetic potential and performing at the top notch that it can perform when it's present compared to if it wasn't in the system.
Wendy, what form of silicon would you add to a system, a hop system, for the best response?
That I don't know. And that's one reason why I'm going to be putting them out in the gardens this year, is to try and understand what the best way is to feed them and to grow them with the different forms that I have. So at this point, I'm not sure how to answer that question.
Okay. This is what we're going to do. We'll see what you think of it. So monosilicic acid in a complexed with a humate and an amorphous foliar nano type. Do you think?
Yeah, I think that would be great. With the complex, I would make sure that you have a really high concentration that's in a higher concentration in the soil profile because you're putting it in the soil, correct? With the humic.
Both.
So
yep.
The hops are going to take up a high concentration of silicon, so they're borderline hyperaccumulators. And so you want to make sure that you have a higher amount in there. And that's what's nice about coming in with that foliar spray, is that you may induce more weathering of the product that's down in the soil system. So again, you are likely going to get it from those two different areas coming up through the roots and in through the leaves. So I think that would be an excellent start to see.
Well, I think we have the opportunity to do both and each. So you would probably be interested in.
And honestly, that also ties back to what type of soil or what type of media they're growing these in, because that might have a big impact too, to where you could get away with just doing a foliar application. If the soil profile is going to provide some of that to where you wouldn't need to incorporate it into the soil as well. Or if you were to take out the soil or the foliar application and just do the soil, having it down there is going to be important. So really any of those scenarios, as long as you're going to have enough that's present within that profile to grow those plants at the amount that's needed in the different tissue.
Right. At this point, he's not adding any silica products, so it's all going to be new and a new adventure. So I'll keep you posted on it.
I would love to hear follow-up on that.
And I want to taste the beer because I haven't been paying attention since Wendy said silicon helps hops, which IPAs, because that's my favorite beer, IPAs, Nectar of the Gods right there. Yeah. Love IPAs.
It's great.
Yeah, Wendy, when I was living in Ohio, a buddy of mine, he put in about a 1/4 acre of hops. Has hops taken off over the last 7 or 8 years, or has it kind of remained flat? Are more growers doing hops in Ohio yet or not?
I don't know because my little brother is a home brewer, and so he kind of twisted my arm, really asked me to get some into the garden. And as I looked into it, saw that there wasn't a lot of research in on it. But I don't know if it's more for like the hobby gardeners. Mm-hmm. I see them around here a lot more so in people's larger backyards than we do fields of that. So I'm not sure what the market looks like here in Ohio. I'm sure it's growing because I know the craft beer industry and the microbreweries, all of that is really getting large in our area. And so I would assume that if it isn't growing yet, that it will be in the future.
Okay. Excellent. Is it 5 o'clock yet? Because I could really go for an IPA now. Okay. I'm gonna deviate from silicon here for a moment. I saw something the other day. This was a new concept to me. I saw you liked this post too on LinkedIn. Biochemical sequence of plant nutrition. And I saw silicon listed on there. I'm unfamiliar with this. Do you recall that post? And I do
not recall that post.
It had something to do with starting with boron, then silicon. It was like this sequence of how plant nutrients are just building upon each other. Maybe we can revisit it. I saved it.
Okay, I'll have to look back through. The thing is, anytime someone brings silicon into the light when they're talking about nutrients, I always fully support that because a lot of times silicon is left off of that list when they're going through. So I'll have to look back on that.
Yeah, it was like this cascade effect when it was right. Really cool. And I'll send you the link too because I started going down that rabbit hole after I saw it, and I saw that you liked it. I was like, oh, there's got to be something here if Wendy liked it.
So that might be something that I liked, and I downloaded the article, and I just have not gotten back, especially if it was in the last week or two. I have like 10 articles that I need to get through and read.
Same. Okay, you sound like me. I just built a Google sheet of all these articles. I'm like, oh, that looks interesting. I don't have time to read it. I'm just going to save the link. And that was one of them.
Full right now.
Yeah. Okay, something came up for me as we were talking, and I was curious to know if other than silicon, if you were working on something new. But then I remember from a previous meeting that you went to, and it may have been an AFCO meeting, anything new on the horizon. And your chemistry knowledge is better than mine, and I have a kind of an ongoing debate with my family. It really doesn't matter at the end of the day, but I tend to get specific. Is it iodine or iodine? Technically, do you know?
Gosh, I'm a biologist.
Yeah. Well, the reason and I do it just to kind of get my family riled up because I said, well, because one of our children had to do something with iodine, and they're like, oh, it's iodine. I said, go grab the periodic table. Yeah. Why? I said, look at what family it's in: chlorine, fluorine, iodine. They're like, oh, come on, Dad. I said, I know. I'm the only one in the universe other than my chemistry professor in college is going to call it iodine. Everybody else is going to call it iodine. Just like there's no comma in the when you say the Pledge of Allegiance.
Well, chlorine and chloride. What are you talking about?
Right.
Are you talking about the element, or are you talking? It's probably right along that. And I'm not a chemist, so don't.
All right, we got to have a chemist on then.
There you go.
I'll back up though. Is there anything new for you on the horizon, or something that's caught your attention, interest, that may be kind of the next big thing?
No, silicon's kind of my big thing right now.
Yeah, there's still a lot of potential there for sure.
I have more than enough right now understanding the cellular and molecular response. And so what I've been doing is I've really been getting heavy into microscopy, mainly because I want to know when we talk about silicon and we talk about its response, a lot of times, and I might be generalizing this for other people, but when I think, when I was learning about silicon in the leaf, I'm thinking that the whole leaf, that every single cell in that leaf has the same function. But we know that in these organs, different cells play different roles. And so I believe that there are groups of cells that are important for silicon that I'm calling silica cells or silicon cells. And if we can identify where these cells are located, we can start trying to understand what those cells are involved in within that. So just like if we want to understand circulatory system, we want to look at heart muscles, we want to look at veins. We don't want to look at the entire torso because there's a lot going on in there. And so with microscopy, I've been looking at a lot of leaf surfaces to understand why some species take up more silicon than others, especially within the dicots. And so I've been trying to get more into the cellular, back into the cellular molecular ideas. And that's on my horizon, because we know silicon works. When it's not there, I can tell you to go put it out. We're fairly comfortable with these different plant species. If you know it's similar to another species, you can give similar rates just like any other nutrient. But it's that why. That why is what drives me. What is going on inside? How is it working? We know the effects, but we don't know specifically where that silicon element is working, what protein it's involved in, if it's involved in an active site of an enzyme, what's actually going on. So that's really what I will be going into and my diving deeper, which kind of puts me outside of the realm that I'm in right now. But the education is the other big thing, bringing it into light to look at silicon as a nutrient. And that really, I think, is those two are my co-number ones on what I'll be doing for the rest of my life, I think.
Yeah,
unless we can get it done
both equally
faster.
important, and I'm so thankful that you're doing it. You are cut out for this.
Yeah. I was bitten by the bug, and I don't regret it. I almost said I regret getting into it, but I absolutely love what I do. And it's an amazing element that when it's given in the right form at the right time to the right plant, does just absolutely amazing things. And the fact that we still don't recognize it, and it's not as well known, that is what pushes me to do what I do and continue to do it.
Fantastic. Well, it's great. I'm so glad that we got connected all those years ago, and that you're continuing to do what you're doing. And I think there's going to be more opportunities for us to work together on certain things. And I know you've got other projects you're working on. So that being said, since you have now ventured out on your own, and I know you have no shortage of things to do, but how can people find you? Maybe obviously on LinkedIn, right? But are there other ways? Do you do any type of social media, or what other than maybe going on LinkedIn? What's the best way to reach out to you?
So I, again, as a scientist, I'm really, really bad at social media. I do have an Instagram page, and I don't even know what my name is on that, where, I'll post microscopy pictures. I'll post just random pictures. And I have a Twitter account, but I don't use it. So LinkedIn is probably the best way to get a hold of me. I haven't built anything up yet for the business because it's been less than a year since I've started it. And so if you get a hold of me on LinkedIn, or I'm still with the University of Toledo, you can find me through their websites and get a hold of me through them as well. And those are probably the fastest ways. I don't know, I'm usually at some of these trade shows around, but not so much out in the or the western side of the states.
Excellent. Yep. Great. Well, very good. Josh, Bill, anything else?
No, I think all my questions were answered. Thank you.
Wonderful.
I just want to say thank you to Wendy. I've just kind of been riveted writing all this stuff down, and just going forward, I'll keep you posted on our thoughts, and we maybe through Johann we'll design some things, and so you can gain some insights too in the hops world.
That would be fantastic.
Yeah, we have no shortage of hops in this part of the world. It's a very big deal. So anyway, thank you, Wendy. That's all.
You're welcome.
Thank you very
and thank
much.
you all for having me.
Yeah. We are honored that you chose to come on our podcast as your first podcast guest experience. Dr. Zellner, we appreciate it.
Oh.
And we'll be in touch.
Okay, sounds great.
Okay, take care.
All right.
Thanks, Wendy.
You too.
Thank you.
Yep.